Hello, everyone. My name is Lisa Ewan from Northwestern Polytechnical University. Today, I'm excited to present our research titled Hybrid Global Local Representation with Augmented Spatial Guidance for Zero-Shot Referring Image Segmentation. Recent advances like Segment Anything Model (SEM) and CLIP enable zero-shot learning, performing RIS without category-specific training. Typically, SEM generates candidate masks, while CLIP matches their visual features to text descriptions, selecting the best match. However, key challenges remain. Mask feature inaccuracies. Most methods extract features only from target regions, ignoring contextual cues. This limits their ability to handle similar objects or complex descriptions. Spatial misalignment. Phrases like left of the tree or next to the bicycle often fail to align with visual features, causing errors. Incomplete segmentation. Occluded or multi-region objects may result in partial outputs due to ambiguous matching or lack of global context. As shown in this figure, these issues lead to flawed results. Our method aims to resolve them. In this slide, I'll give you a quick overview of our proposed framework. Our method consists of two key components. The first is a hybrid global local feature extraction module which enhances the mask feature representation by integrating both local and global contextual information, all without requiring any additional training. Specifically, we designed two complementary branches within CLIP. One focuses on the local region of the mask, capturing detailed appearance features, the other captures broader context from the entire image. These global features are progressively fused into the local branch to generate a more enriched and accurate mask representation. The second component is our spatial guidance augmentation, designed to better capture spatial relationships described in referring expressions, such as left of, next to, or in front of. This module introduces enhanced spatial cues including spatial relations, positional encoding, and coherence modeling, which help align the visual and textual features more accurately. Together, these two components work to overcome the limitations of existing methods and significantly improve segmentation accuracy in zero-shot settings. Let's explore our hybrid global local feature extraction approach. It merges local and global visual features for every mask proposal. Local features highlight the details within a mask, whereas global features grasp the overall image context. Combining them aims to provide an accurate and rich representation of the object. Starting with local feature extraction, its purpose is to get detailed visual features for each mask. This is done by applying a binary mask on the input image, creating iLocal equals I multiplied by mi. This ensures only the target region's pixels are used for feature extraction. The masked image then goes through the CLIP image encoder to produce high-quality, region-specific features that capture essential details like texture and color, vital for matching with text. A key difference from other methods is that we preserve the image's full size and just mask irrelevant parts instead of cropping. Keeping the full size helps maintain spatial alignment with the global features, crucial for effective feature integration later. Now, let's move on to the second component of our framework, the global feature extraction. While the local branch focuses on fine-grained details within the mask region, the global branch aims to capture the broader context surrounding the object. This helps the model understand not only what the object is, but also where it is located in relation to other objects in the scene. To achieve this, we start with the original image and apply a Gaussian blur to the non-mask regions, denoted as phi blur. This operation suppresses irrelevant background details while still preserving the essential spatial structure around the target object. But that's not all. We further guide the visual encoder by introducing an attention mask during the self-attention computation in the last L layers of the CLIP image encoder. Specifically, since the class token serves as the final visual representation that will be aligned with the text embedding, we nullify the attention scores between the class token and image tokens outside the mask region. This effectively prevents background regions from influencing the visual feature of the target object. Now, let's look at the third and key part of our framework, hybrid feature extraction. The goal is to combine local and global features in a way that improves mask representation without losing focus on the target. The local branch captures detailed appearance of the mask region, while the global branch provides context from the surrounding scene. We fuse them progressively through the CLIP encoder layers, allowing the model to learn how to best use both types of information. A token mask is used during fusion to ensure only the image tokens within the mask region are considered, avoiding interference from irrelevant background areas. This hybrid feature is passed through the encoder layers, with fusion happening at each step. In the final layer, we get a refined feature that includes both detail and context. We then compute the cosine similarity between each hybrid feature and the text embedding from clip. The mask with the highest score is selected as the final result. Now let's move on to the first part of our spatial guidance augmentation. One key challenge in zero-shot referring image segmentation is handling expressions involving spatial relationships, like at the pizza on man's right. To address this, we parse the referring expression into objects and their spatial relations. We compute a semantic alignment score for each mask proposal using cosine similarity between the object's text embedding and the mask's visual feature. We select the top K masks and normalize their scores with softmax. Next, we define a spatial relation function R to check if the spatial relationship is satisfied based on the positions and sizes of the masks. Finally, we combine semantic alignment and spatial consistency into a final spatial aware score that re-ranks mask proposals by considering both object match and spatial constraints. If no spatial relations are mentioned, we use the original semantic alignment score. To further enhance the spatial coherence of our segmentation results, we generate a spatial localization guidance map G company. This map helps to identify and highlight the target region based on the referring text feature T. Specifically, we leverage the self-attention mechanisms within clip to compute the similarity between the referring text feature and each visual token embedding derived from the clip image encoder. The process follows GEM proposed by Buselam et al., which effectively uses self-attention for expression localization and segmentation. Finally, we introduce the spatial position guidance, which further enhances our model's ability to understand and localize objects based on explicit positional cues in the referring expression. To incorporate spatial positions, such as top, bottom, left, right, or middle, we define a set of positional guidance matrices GPOS. Each matrix corresponds to a specific spatial attribute. For example, the top matrix emphasizes the upper portion of the image. If a positional keyword like top appears in the referring text, we apply this positional guidance matrix to refine our earlier spatial coherence guidance map. The combination is done via element-wise multiplication. This new guidance map G highlights regions that are both semantically aligned with the text and spatially consistent with the described position. Next, we compute a spatial guidance score for each mask proposal, defined as the difference between the average guidance value inside and outside the mask. Finally, we normalize both the semantic alignment score and the spatial guidance score using softmax and combine them into the final mask score. Now, let's take a look at how our method performs compared to other state-of-the-art approaches. As shown in the table, our method achieves excellent results across all three datasets. Notably, we achieve comparable or even higher mean IOU scores than methods that require additional training data. This is significant because it indicates that our approach is not only effective but also highly efficient, achieving strong performance without the need for extra resources. Our balanced consideration of both semantic alignment and spatial coherence allows us to handle a wide variety of objects more effectively, making our method robust and versatile across different scenarios. This demonstrates the potential of our proposed framework to significantly advance the field of zero-shot referring image segmentation. As shown in the visualization results, our method produces more accurate and context-aware segmentation masks compared to existing approaches. The ablation studies reveal that our proposed mask feature extraction method outperforms alternatives across all three datasets. The optimal starting layer L for hybrid fusion enhances model accuracy on the REF-COCOG dataset. Incorporating different types of spatial guidance further improves segmentation quality, demonstrating the importance of each component. In summary, our work introduces a novel hybrid global local feature extraction method for zero-shot referring image segmentation that significantly improves mask representation without requiring any additional training. By leveraging CLIP and SEM, we effectively combine detailed mask information with broader contextual cues. Furthermore, our spatial guidance augmentation strategy utilizes spatial relationships to reduce segmentation ambiguities, ensuring masks are accurately aligned with referring expressions. Experiments on 4 public datasets, including RefCOCO, RefCOCO+, RefCOCOG, and 1 more, demonstrate that our approach outperforms current state-of-the-art methods in zero-shot referring image segmentation. For those interested in exploring or using our method, the code is publicly available at GitHub. Thank you for your watching.